week 7, potential energy and kinetic energy. And we have been talking about work and energy. Energy is the ability to do work, or if you look up in dictionary, it says vigor or capacity or the power, and that all relate to the energy. But scientifically, in the physics, energy is the ability to work. And then what is work then? And the work is the process of the energy transfer. And there are all different forms of work, and so do different form of the energy. So in the mechanical physics or in Newtonian physics, work is defined as force times distance. And then we had the work and energy theorem, which is energy gain is of an object is equal to the kinetic energy increase. So that's similar to that momentum impulse theorem. And an impulse is equal to the momentum change. Now here the energy gain is equal to the kinetic energy change. So the interpretation of this is if you have a force applied to an object, then for a certain distance, then that work is simply this times the distance. And the physics interpretation of this process is that whoever applied this force and provided the energy from their body or chemical energy turned into mechanical energy. And then through the work of force, then the energy goes into the kinetic energy of this object, or the kinetic energy in turn lost into friction between the up block and the ground. So all that is good. So now there are 4 phases of matter: solid, liquid, gas, and plasma. Solid have the definite shape and volume. The molecules are relatively fixed distance from one another. They sometimes organized in a very nice array like this, and we call it crystal. And for example, a silicon atom, and the most abundant substance on Earth, is ordered like a hexagon structure if you look from one profile. And then they bond together in the solid. They are very close together. Liquid, on the other hand, the molecules are still close together, they bond together, but they can move around. From outside, look macroscopically, and they don't have definite shape or volume. They can flow around each other like water. Okay, but if you zoom into microscopic world, which means and the molecules are still close together. They are packed, but they can just slide around each other, but they can't move around. But it's basically close packed. That's the general picture of liquid. Gas is different, and when the temperature is high and pressure is low, and then this phase, there are weak cohesive forces between molecules, or rather the kinetic energy, the motion overwhelmed the attractive force, so they are separate into the space around it. They have no definite shape or volume, and they move in random directions, and the speed and are influenced by their collisions. So that's the picture you have. And you can see a video, or in the lab, we see that's the general picture in a gas. Well, in other words, there's a lot of space between molecules or atoms. They move in different speed, different directions, they collide, or they bump into each other all the time. But they have a speed, and here's the word. If the speed has different and random directions, we say mathematically we have a speed distribution or velocity distribution. Another phase, the fourth phase is the plasma phase. And plasma means something just smeared out in general. If you look up a dictionary, it means just And then here, particularly, it means positive, negative ions, which means they are separate. You know from chemistry that in normally substance, the positive protons are surrounded by negative charged electrons. They are very close together. Okay, if we rip off the electrons off from the core, from the positive core, they separate, then you get ions. So in this case, the plasma is gases, but they are basically ion and electrons, and normally very high temperature. And they conduct electricity and interact with magnetic field. So these are the situations that can create electrons. So you put a grape into microwave because the conducting material, so it's so hot that you get this ion. That's actually plasma. But usually we experience three different type of phases: solid, liquid, and gas. Plasma, you can make it in special situations on Earth, like this toy you probably see, and this in the microwave. Sometimes things turn into plasma, but just momentarily. But if you look into study astronomy and astrology, not astrology, astronomy, in sun, in some other stars, basically all plasma. Okay, so it's not uncommon actually. Everything on the sun is in the form of plasma. Converting temperatures. We have been talking about the temperature is nothing but the kinetic energy of the molecules, or average of the kinetic energy. The real characterization is connected to the Kelvin degree. Basically, is average of the kinetic energy of each molecules. But velocity is very fast, but average is regular number, squares, always positive number, but the mass is very small. So this temperature, the kinetic energy, is very low, very small. Now to scale up to a more comfortable number, can be used for our daily life, and Boltzmann et al. Used a conversion constant, and this Boltzmann constant, which is a very small number. Over here, that's kinetic energy of average molecules, but divided by a small number, so let's scale up to some regular numbers. Not only that, this number is chosen such that the temperature, the Kelvin degree, has just exactly 100-degree difference between the ice point and the boiling point. And in particular, at ice point is 273.15.
Hi, this is Frank with A Plus Security Center.
And 1.5. And then at the boiling point is 300.75, exact 100-degree difference. If I ask you why exactly in Kelvin degree there is a 100-degree difference, and you have to ask Boltzmann, and you can say, well, it made that way because it adjusts this constant, so this new temperature scale, it is kinetic energy but scaled with a constant. So the constant is fixed. You can look up the Boltzmann constant value, which is something very tiny number, but that will scale this temperature to the Kelvin degree. And characterize the Kelvin temperature is that 0 degree is absolutely no motion. So then it's no velocity. Everything is dead. So, but can you have a negative Kelvin degree? No, because something squared over here can never be negative. And then, so at worst case, everything is frozen and not moving, it's 0. So, and of course everything is go. So therefore Kelvin degree is always a positive number, and lowest is a degree. So now associated with that, then there's a Celsius degree temperature. And if essentially it is Kelvin degree, but I just don't want to use this number, 275.15, you say, well, that's the freezing point. Let's call that 0 for Celsius. And then degree for degree match, and then every time Fahrenheit go up 1 degree, Celsius go up, and then the Kelvin go 1 degree as well. So therefore, Kelvin temperature and the Celsius temperature are essentially the same temperature, but except that the Celsius are invented to make it convenient. So 0 is the freezing point, 100 is the boiling point, and so on. So then we have the conversion between Celsius and Kelvin, pretty easy. So simply self plus this number, and you get Kelvin. And backwards, Kelvin to Celsius, subtract 275.15. So, and vice versa. So that's the conversion. And then we have Fahrenheit temperature degree, and that is the empirical temperature, and it's characterized that its freezing point is some kind of a salt water, the water you use to make the pickles, and when you add that kind of salt into water, its freezing point is very low. It's below where ice freeze. So that point is Fahrenheit degree 0. So, but turned out that that became the most popular temperature we use in US and some other English-speaking or Canada. So then Fahrenheit converting to Celsius, and then you have this formula. But one teacher point to remember is that 32 degree Fahrenheit is freezing point, and then something like 212 is the boiling point. So these are the two formulas. So now we mentioned the 3 different temperatures. Out of the 3, you have 3 choose 2, and you have 6 different conversion relations here. So remember, I'm not asking you to force you to remember exactly, but just get the concept. You can remember easily. Whenever there's a test or something, these conversion formula are available and easy to use, but then it's good that you can remember it. All right, that's it. So this is the recapture what we talked about in the class. These are the temperature feature point, and 32 degree. Let's talk about the Fahrenheit first. 32 degree Fahrenheit is the ice point, and boiling point is 112 degree Fahrenheit. Actually, I myself is not quite familiar with this, but well, Imani, she knows. And then fever, and what temperature considered fever, and you say 102, and that's cool. And what's the normal temperature is around 98. So that's the Fahrenheit, and the temperature that we most familiar with here in United States. And so then Celsius. Celsius is nothing but absolute temperature rescaled. Ice point is 0, and 100 point is the boiling point. And with fever, and that's good to remember if you go to another Europe or Japan or China or any other Asian country, they use Celsius. So 37 degree is low fever, and temperature 37 or 36, and 39 is kind of high fever, 40 is even high, 42, you better watch out, it's very dangerous. Normal temperature is about 36 Celsius. And Kelvin, and of course, once again, 273.15 positive is ice point, and then add another 100 degree Kelvin, you get 373.15, and that's the boiling point. And then if you want to see what the absolute temperature from Celsius, all you have to do is add this magic number, 273.15. So we did a conversion between numbers. So this the formula is still in the previous slides and pages. And from Fahrenheit to Celsius, you simply do 5/9, which is a very almost half, and then parentheses Fahrenheit minus 32. So we tried with 0 degree, so you have 0. And then the other way around, backward from Celsius to Fahrenheit, you have 9/5. Usually, and also just remember that the Celsius is larger step. So therefore, and 9/5 is about 1.8. You multiply that, and then plus 32, because the 0 point is at 32 in Fahrenheit, and Celsius. So you, for example, 32 degree, that's a little bit low fever, and then you have 32 times 5.9, and then plus 32, and then you end up with something like 102.2. So you will get this question. These are simple questions. I'm sure I encourage you to get all of these questions answered correctly if you ever you've ever been asked these kind of questions. Converting between temperatures. Kinematic gas theory about temperature and gases. And you can start this video and simulations from these links if you had a real slice. And now let's recall, the temperature is nothing but kinetic energy of atoms and molecules due to the translational motion, and that's energy. Okay, and that is done in the previous slides. Now we focus on a system of gas and its pressure. And what is pressure? And pressure, I think about its force on a surface and on a unit surface. The pressure will be force divided by the area. So, and now here in a gas system, the forces actually come from the collisions of these molecules on the wall. In a gas system, there are millions of molecules and collide. So therefore, pressure will depend on the kinetic energy, and in turn, kinetic energy depends on the temperature. Therefore, the pressure will depend on the temperature. And in your intuition, in your mind, see, the higher the temperature, the faster the balls will move, and then it will be hitting the wall harder, and therefore the pressure will be higher. So if everything else is fixed, you will expect the temperature-pressure relation will be linear increase relation. So that's reflected in this equation, and this is called ideal gas law. And if you think about everything is fixed, so if temperature goes high, which means the speed goes high, we hit it on the wall, and we'll have a stronger force. If everything else is fixed, and pressure will go high. And again, temperature go high, speed is high, and pressure go high. Now what about the volume? So the volume, the same, everything is fixed. So if the temperature is fixed, you can divide this volume to the other side, and you will see the pressure and volume has a reciprocal relation, which means inverse. Pressure depends on the inverse of V, which means volume goes up and pressure actually goes down. And the other way, if volume goes up, pressure will go volume goes down, the pressure will go up. Because think about it, the pressure is nothing but the collision between these walls on the surfaces, and if the volume goes up, go bigger, and the box become larger, the area will be larger, and the same number of collision, the force will be less on each unit area. So you have more area, and therefore pressure will be low. Okay, so if the box is bigger, pressure will be low because you have same ball, but it will spread out in bigger areas. So that's fit our imagination. So if you have a volume goes up, then pressure goes down, and pressure goes up and volume goes down, and vice versa. Okay, so they have an inverse relation. Now, here's another factor, and N. N is number of moles, or the amount of gas in the box. And what that has to do with the pressure, and you can think about it. So you have the box, temperature fixed, you have the same average velocities. Well, imagine you have 3 balls and it hit 3 times or something. And if you have 4, and you hit more, and the pressure will be higher. You have 10, you'll have more, and you have millions of them. It all really depends on how many of them there. So the dependency with the quantity of the gases to the pressure, or pressure dependency of the quantities between these two, P and N, number of molecules, and is simply a linear relation. So you have more molecules inside of the box with everything else fixed, more pressure, more molecule, more pressure. So that is natural thinking. So everything is within our imagination. We can know everything about this, and then so it's summarized in this relation: P times V equal nRT. So, and then what is that constant? So that is nothing but a constant, a gas constant, and then its value is 8.314, and so that is fixed. So, so this we will solve several problems, many homework problems, to use this equation. So even though this equation can be derived from statistical physics and from macroscopic models of the ideal gas, in fact, it is derived from there, but the details of our mathematical derivation is beyond this course. We are just focused on application of equation, given that we understand why this equation is true. So to summarize the details, P here is in units of pressure, meters per newtons per meter squared. That's units of pressure, and actually unit in Pascal. The volume in cubic meters. Actually, cubic meters is quite big. And N here is mole number, and which how many moles. And once again, 1 mole of any molecule has this many numbers. Okay, it's a lot of molecule, but it's a fixed number. In other words, if you say I have 1 mole of hydrogen atoms, how many of them? Well, 6.03 times 10 to the 23. It's quite a lot. But if I have 1 mole of helium atom, how many of them? Same number, 1.03 and 2 times 10. Actually, 1 mole of anything has this many things. Okay, the same number. But immediately we think, well, how much 1 mole of something weighs? Well, depending on what it is. And 1 mole of hydrogen molecule, hydrogen atoms, will weigh 1 gram. Okay, hydrogen use a standard. But 1 mole of hydrogen molecule, which has 2 hydrogen atoms, will weigh 2 grams. All right, and what about 1 mole of water molecules? You know, water is H2O. So H is 1, another 2H is 2, and oxygen has the weight of 16. So 1 mole of water weighs 18 grams. But they have how many water molecules, how many H2Os, and same number, 6.03 times 10 to the 23. So 1 mole of anything have the same number. That number is called Avogadro number. 1 mole of anything has this number, but they have different weight. Okay, and it's easy to remember. The weight is just its molecular weight and turn into grams. So, for example, the molecular weight of hydrogen atom is 1, and therefore 1 gram. Molecular weight of hydrogen atom is 2. Molecule is 2, therefore it's molar weight is 2. So molecular weight of helium is 4, and therefore, molar weight of helium is 4 grams. So molecular weight of oxygen gas is 32. Therefore, the oxygen is molar weight of oxygen is 32 grams. So and so on. You just simply turn the molecular weight into grams. So that would be a different way. But in any case, 1 mole of anything has this number of molecules. Remember that firmly. And that number is called Avogadro number. So that's the mole number, how many moles of this. And then temperature, again, is in Kelvin degree, and molar constant, we already said 8.3 mole and Kelvin, and also Avogadro number, and that magic number is 1 mole of anything has this number, and 1 mole of anything has exactly this many molecules. Okay, and this is the note on one of the classes, and we just look at the ideal gas law and try to appreciate it. And 3 quantities of the gas, or 4 quantities: pressure and volume and temperature and the amount in mole numbers. So mathematically we view this. So if you think about pressure's relation with temperature, you think about one is fixed, and then you will say, well, pressure is actually a function of temperature, with everything else fixed as constant. Implies that volume and molar number and of course gas constant is fixed. And then you will expect that linear relation goes out. Temperature goes high, pressure goes high, everything like that, just straight. And temperature goes to 0, pressure goes to 0. You can imagine the atoms stop moving, and then there's no hitting on the wall. The pressure goes 0. So now, if you solve this V into the other side, then you try to look at the relation between the pressure and the volume. You have an inverse relation, pressure and volume. So divide this to the other side, and RT divided by volume. Then this relation is reciprocal relation. So volume goes up, and then think about it. Everything else is fixed, temperature and the amount, and then volume goes up. Then you will have bigger area on everything, and they have the same force because they have everything else the same, and the area same force, bigger area, the pressure will low. And of course, if everything, the volume goes small, then you have a small area on the wall, and then same force, then the pressure will go high. So it's an inverse relation. So it's put like this: your volume goes up, area gets big, and pressure goes low. And volume goes small this way, and of course everything's squeezed, and the pressure goes high. So that's just this trend we talked about in class. Well, in one of the classes we re-enhanced on the concept of PV equal nRT, the ideal gas law. And think about introduce the effect of the gravity. So, and air molecules are pretty close to the ideal gas, but if you look at a small box of it and still follow the ideal gas law. But when the gravity is introduced, and imagine on the Earth's surface, there were molecules, and they are actually, and you were asked why it's not going away. So it's going that fast at 300 meters per second, like speed of rockets, and goes very fast. But because it would go flying away to the outer space. But why is it not flying away? Because the gravity attracting it. So there are 2 factors. One factor is there are high speed moving randomly, but on the other side there is another factor, which is the gravity as you bring them down. The balancing effect that will all attach to the Earth but does not fall down to the ground because they kick out into space. Then they spread out or into about a certain distance above the Earth. But that distance, if you look from the bigger scale, is not very high. But of course, compared to us, each of us is just a few feet tall. It's very, very high. Looks like the air is infinitely high, but actually it's not. It's not that high. It's about 10 to 15 miles. Okay. So you can think about it's have a column of air covered, or a blanket covered us. So, and then its weight will be all on a ground. So it's gradually the pressure of the air gradually reduced and in an exponential format. Okay, and go to the higher you go, the lower the pressure at the same temperature. But at the bottom, think about all that weight of the molecules on us, and that has the atmosphere pressure because of the weight. All right, of that. So then at the bottom, how much is that pressure? That is called atmospheric pressure due to air. And if you think about 1 meter squared, and that is about 101 times 3 newtons per square meter. So this square meter, all that air is on top of us, and we will have this much force on 1 square meter. How heavy it is? And remember, I asked you in the exam, how strong is a Newton? Like a little apple holding, and 1 square meter will have this many apples, 100,000 apples, quite strong pressure. Well, if you ask you, and why it's not moving, but of course it's in all directions, isotropic. So that's the reason for. So that's because of the gas, and because it has all the weight of the molecules on us, so they have atmospheric pressure. And so this pressure will go low and low, but slowly, and get up. And of course, because the standard atmosphere pressure is also same number, but it has, since it's depending on the height on the top of building, top of a very high building, the pressure will be lower. Then where the standard is at the sea level. At the sea level, and at 0 degree Celsius, and the pressure, so that's the pressure is the standard atmosphere pressure. All right, that's this class, or it was that class. Okay, what we did. Okay, in this class, we actually reviewed a little bit chemistry, or how to understand how to read the periodic table, and how to understand the atomic structure of the every elements. So this is actually a review if you have taken chemistry. So just you have a core has protons and neutrons. Okay. And then proton number is actually, number of protons is actually the name, tied to the name of the elements. So if you have a core have only 1 protons, and then that's element number 1, you get hydrogen. So on each square in the periodic table on top left corner, and there's a number. And actually that's the number of protons, and also you call it number, it's also called the atomic number. And that number is like your number on your jersey. So your player number 1, player number 2, and so on in a team. But in this periodic table team, number 1 is hydrogen. So actually same time number of protons. Then in the middle is the name, it's called hydrogen. And at the very bottom is the weight. Okay, then the weight is 1. Now, if you have helium, and then you will have this picture. There are 2 protons, and therefore on the top left you will have 2, which means element number 2, helium, and He, that's symbol. And then you have a number. So what it is called? It's called helium. And the very bottom end is called a mass number. Okay, it's basically 4, but sometimes it has a little bit of decimals, and that is, but this number at the bottom is called atomic weight, or how much basically is counting the numbers. So 1, 2, 3, 4 for helium, so you have 4, but 4.1 or 4.2, but the bottom number, at least for the first 2 rows of periodic table, and pretty close to a whole number. Once again, the bottom number is atomic mass, and it's pretty close to a full number. For example, helium is pretty close to 4, so therefore it's 4 point something. So that number is 4, which means there are 4, 2 protons, 2 neutrons, and that number is, if you round this number to a whole number, and it will be, we call it its mass number. If you call it mass number, it's 4 exactly. But if you say atomic mass, it's 4 point something. You can read the periodic table. So once again, if you say mass number, it's 4. 1, 2, 3, 4. 2 protons, 2 neutrons. If you say mass of helium is 4 point something, but you round up that number, it goes to 4. So remember what when you are asked a question, you listen exactly what is asked. If I ask you what is atomic weight for helium, you will read the periodic table, all the decimals, 4.022, something like that. But if I say what is the mass number for helium, you round up that number, just say 4, just indicating there are 4 particles. Once again, neutron and protons have approximately the same mass. Once again, neutron and protons has approximately the same mass, but if for our practical purpose, especially for chemicals, and so then, in fact, so just 4, they have problems, they'll count 4 numbers. So therefore, so 2 for helium. So then what, look up, okay, now here's the test. What's for lithium? Okay, number 3, and so number 3, and what if for them, you have here something like 6.9 and with mass, which means 6.9 times of the hydrogen's weight, but it round up to a 7. All right, if I'm over here is a 7 mass number. So if I ask you how many neutrons are in lithium core, you will say 4 neutrons. Why? Where did that 4 come from? Because the total is 7 minus 3 protons, and then what's left is neutrons, which is 4. So hope that makes sense. And then these 4 quantities have the same number. Remember, the weight of a hydrogen atom has this much weight, 1.67 times 10 to the negative 23. So that's weight. Okay, and this number, or approximately this number, called 1 atomic weight units. Okay, this weight is called 1 atomic weight. It's very small. But if you have 2, then of course 2 atomic weight units is very small. And so now, what about the weight of a neutron? Same number, of course, maybe 1.66 or something, 1.662, but same number. And 1 atomic unit is weight. So the 4 quantities when people use referring to in any practical purpose, for us, we are not getting to detailed nuclear physics or something. And these 4 refer basically the same. So remember, weight of mass of hydrogen atoms and 1 atomic unit weight, and this number, and the mass of neutron and mass of proton is all referring to the same weight. So therefore, simply it was 1 atomic units. And the 1 atomic units is some number, and you can dig up on Google, and this number is all about the same weight. And it was listed here on the bottom line of every element. How much weight is that? How much mass is the atom is measured compared to how many of these weight. So therefore, this is that used as a units. Or you can say how many times heavier than the hydrogen atoms. So for example, helium is 4 times, lithium is 7 times, and so on. Oxygen is 16 times of that. So it's atomic mass units. So atomic mass units and weight of proton, weight of neutron, and 1.67 times 10 to the negative 27 is all more or less the same number. Well, if you are after the difference between these 4 numbers, and then great, you want to be a great scientist, I encourage you to study physics, nuclear physics, and think why there is slight difference between the actual counting numbers, and that will involve in nuclear reactions and really beyond this course. But that's what I have to offer here. Just think about these 4 concepts are the same number. Once again, the weight of a hydrogen atom, and weight of mass of a proton, and mass of neutron, and atomic units mass, and 1.67 times 10 to the negative 27 kilograms is the same number, right? Well, for important concept, it doesn't hurt to have some repetition. So now let's talk about this molar number. I have said that 1 mole of any substance has this many numbers. Why is this magic number? So it's not really magic at all. Let me illustrate about this. So you say, well, if I want 1 mole of hydrogen, 1 gram of hydrogen. So if I have 1 gram of hydrogen, so you have 1. Okay, and if I want to say how many of hydrogen atoms are there, but I know the hydrogen atom has the weight of, that's atomic weight, basically approximately 1.67, okay, and times 10 to the negative 27, so we just talked about kilograms. That's also the number of neutrons, the number of protons, and so kilograms. So, and times 10 to the, of course, if you times 10 to the third, right? 10 to the third kilo. Okay, and if you divide this 1 over, you use your calculator. So 1 gram of hydrogen, and you divide by this units, which means 1 gram is how many of this little weight? Well, it's a lot. You invert. Each hydrogen atom weighs this much. Well, okay, and but then 1 gram, and you divide this, it will have this many hydrogen atoms. So this many hydrogen atoms, right? So think real hard. So then you get this. You can do the math. You get this 1 divided by that much, and then so then this magic number is really not really magic. It's nothing but a unit conversion. You know, hydrogen atom weighs this much, and then if you divide 1 gram of it, and then you will have this. So then I ask a question a little bit reversed. How much 1 gram of hydrogen, 1 mole of this number, we call this number a mole number, 1 mole. Okay, how much 1 mole of hydrogen weight? How much this number of hydrogen weight? And the answer is 1 gram. Duh, you just made that way, right? So, okay, this many hydrogen atom will weigh 1 gram. Okay, and so that's called 1 mole. Therefore, 1 mole of hydrogen atom will weigh 1 gram. Okay, which means this many. So this is called 1 mole. Okay, this many. Okay, not this many. 1 mole of hydrogen atom weighs 1 gram. Because why? Because that's simply a conversion between units. You get this. So now, if you have a molecule, hydrogen molecule form air, okay, H2, and so if I say, well, this many hydrogen atom weighs hydrogen molecules, H2. Okay, you have this many, 1 mole. So 1 mole, which means that many. Of course, you have double this weight. Therefore, you say, well, this hydrogen molecule of 1 mole will be having 2 grams, right? Because this many is 1 gram, and this many is 2 grams. So now, same idea. If you have H2O, this one, each one has 1, but that one has 16 atomic weight, which means 16. That one has 1 times 2. So therefore, 16, that is bigger. So 1 mole of this, which means this many of this. So if you 1 mole of this weighs 18 grams. All right, 18 grams. 18 grams is quite a lot. So it's water is like several big spoons of water. So 18 grams. So not 3 or 4. So then how do you? So then 1 mole is the mole number is simply a conversion between grams and atomic units. So that's a Avogadro number. Therefore, naturally, to turn the number of mole into the atomic molecular weight is pretty straightforward. You simply do the atomic weight turn into grams. So 18 atomic weight will turn into 18 grams. So we have here some examples. Okay, the kind of molecular weight, okay, is like molecular weight or more molecular weight or molecular mass. Okay, you turn molecular weight to molecular mass. All right. So for example, you have methane, which is carbon H4. So if you look up carbon, the molecular weight of carbon, atom weight of carbon is 12.001. In this case, you really want mass. So which means there are approximately 12 of these mass units. So it's one of them. Okay. So therefore, you turn this into gram, you will say 12.001 gram of carbon. And then you have hydrogen, which is 1.007. You look at from the periodic table, it's this exactly this one. But you have 4, so times 4, you have this much grams. Therefore, molecular mass of this, of methane, is carbon 12 and H4, and you have 16. So 4 of this and plus 12, 12.11 plus 4, you get 16. So that's the molecular mass or molar mass. So molar mass of the methane is 16.043 grams. Okay, gram is the sizable units, but atomic units is very small. But this one is measured in atomic units, and so that's probably you need a molar number. So simply convert this number to mass number. So here's another example. I don't want to go into it. And you have H2, H4. And so what if you have carbon 14 methane? Carbon 13 would be not C12. Okay, C12, you can have C13. So you do the same, where the molar mass will be different. So that's the idea of a molar or molecular weight or molar mass and what's their relation. Okay, molar mass is how much mass is of 1 mole of some substance. And that's a very practical concept. Once again, molar mass, usually in grams. 1 mole of something, how many grams in there? So for example, molar mass of water is 18 grams. It's like 2 spoons of water. So that's the review in one of the classes. And then standard atmosphere pressure, and is this much. Imagine 1.1 over 0.3 kilopascal, and it's because of all columns of water, columns of gas. And of course, pressure changes with temperature. Then this number is this much, and the standard has to be 0 degrees Celsius and 273.15 Kelvin. And 1 mole, and also at a standard using ideal gas, 1 mole of gas, any gas, at the standard pressure, we will have 22.4 liter. Okay, and so that's the summary. This is a review, or looking at the molar number, or Avogadro number, or standard atmospheric pressure from a slightly different angle. And plus, you learn how do you calculate the molar mass from atomic weight. Okay, and look it up from periodic table. We also discussed the units and measurement of the pressure. So standard units is Newton per square meters. That's called Pascal. In fact, that's very small units. Think about it. A Newton is like a little apple holding in your hands. Okay? But 1 square meter is quite big. Okay? And then, of course, 1 Pascal, therefore, is a small pressure. But normally, we don't use Pascal as units. But so nevertheless, that's the standard units, is Pascal, 1 Newton per square meter. So more often we use called PSI as our units, but pounds per square inch. Actually, that's a relatively large pressure. So you think about a 1 pound per square inch, 1 pound force per square inch is like 6,000 some Pascal. You can say around one. That's quite 1 pound square inch, and you have 1 pound. So you feel how strong that is. So then you have that, and then there's another units which is interesting. It's standardly used in weather forecast called 1 bar. Actually, it's a large pressure, and it's like at 100,000. Okay. But imagine the atmosphere will give you pressure, and your surrounding you have pressure of the air by default, and it's 101. So therefore, how strong is the bar? And roughly, you're going to say roughly 1 atmosphere pressure. That's why probably people call it 1 bar, because the 101 is 1% difference from if it's 101.3, and that's basically atmosphere pressure. So therefore, 1 bar is 100,000 Pascal. Exactly. Okay, that's the definition of a bar. But how strong a bar is? It's basically 1 atmosphere pressure. A little bit less, because atmosphere pressure will be 101.3, 101.3, something up and down with temperature and pressure, but roughly this number. So 1 bar is atmosphere pressure, roughly. And then, of course, standard atmosphere pressure is about 101.3 kilopascal. So, but then convert to PSI is like 14. How strong? If you want to have imagine how strong the atmosphere pressure pressing on you, it's like if you have the tip of the thumb, will have like 6 or 7 pounds, or because 1 square inch. Will have 6-7 pounds. You're holding your finger with 7 or 6 pounds. That's not a big pressure, but quite significant. So that's this. And another quantity is we frequently use, we measure the pressure on the tire, is called the gauge pressure. Because you don't want to confuse yourself, or you don't want to keep on saying, oh, there's by default, how much the pressure is actually higher than the regular atmospheric pressure. So therefore, the gauge pressure is actually the amount that above the normal pressure. So you say you blow up a balloon, so the pressure is actually higher inside the balloon. So if you gauge that pressure, which is 14 psi and plus say 14.7, that will be 0.7, 15 will be 1 above atmosphere pressure, and 20 will be 6 psi above atmosphere pressure, because therefore the gauge pressure is how much is above atmosphere pressure. Okay, that's called a gauge pressure. Once again, the gauge pressure, you use the pressure gauge or the meter, and you measure pressure of your tire, is not the absolute pressure, is how much is above. So then you have this relation. So you measure from the gauge, say 5 psi. Then what is the real pressure is 5 plus 14.6. That's the real pressure. So for example, and here, if your gauge says 32 psi, that's what's the pressure of the tire, okay? But actual pressure is higher because there's already by default the 14 psi there. So plus this, your 32 psi, the actual pressure is 47. So 34 plus 14 is 47. That's a pretty simple idea. But just the idea, the gauge pressure is how much above the atmospheric pressure. Or mathematically, it is the other way. The absolute pressure, or you can say the real pressure, is the gauge plus whatever already there, the atmospheric pressure.